Continuing project planning with 10B, we're now going to address what are called scheduling problems. And your learning intention is to be able to do forward and backward scanning, which I'll tell you about, to resolve scheduling problems. Now you know we're dealing with project planning, so the problem will be is scheduling tasks and finding out when they have to start and when they need to finish. Now, the new information here is that our precedence tables have now got an extra column. They're now called weighted precedence tables because the cost or the weight is the time it takes to complete. And in a house building project, it'll probably be mostly recorded as time in days, as you can see here. So, activity A and B, they can start at the same time. One takes 8 days and the other takes 6 days. Now, before we go into any detail, that should tell you without anything else that project B doesn't have to start at the beginning of time. A is going to take 8 days, B is going to take 6 days. It doesn't matter whether that's days 1 to 6, 2 to 7, or 3 to 8. What we don't want is B ending after A, but we do have some flexibility, or float time as they call it, about when to start B. And that applies to many other activities or any task. You need to have some paper and pencil, and in all the examples here in this presentation, I suggest what you do is you pause, see if you can do what I'm going to do, and then play through to see whether you've done it right. So we're going to draw a large copy of this network for the table and then just add weights. So we've done drawing networks before. See if you can add weights. Alright, so the start A and B is 8. I'm going to put that there. And B is 6. I'm going to put that there. Put the arrows in, although it starts to get a bit messy. C follows A and takes 1. Now you haven't got to do that to scale, as long as you indicate that task C, activity C, estimates to take 1 unit of time. D follows B and has an estimated time of 2. E follows C. Now before we go any further, there is going to be a dummy activity. You should recognize that by now. We'll draw in E. Keep wanting to put arrows there. You put an arrow there. E is 3. And a blob at the end to indicate the end of the activity. Keep going down the alphabet. F. Remember we only put in the non-collision activities first, so F is 1 and it starts at D. And notice that G follows E and F, so if we put F like that, 1 unit. We've done that, so we've got G following from E and F. And H following G. And the dummy activity can now go in. F is not only preceded by D, but it's also preceded by C. So there are the two precedents of F, C and D. Dummy activities have a weight of 0, always. And there it is, rather more tidy. Alright, so that's how you add the weights to a precedence table network. In this case they put the letter and a comma and then a number, but it's up to you about that, whatever's tidy. As I said before, we have a concept of float time. Now looking at this diagram, ACE takes 8, 9, 12 units. ACF, which goes via the dummy, is 8, 9, 10. So we have a 12 and a 10. BDF, to get to the same point, only takes 9. So there is some float in there somewhere. The question of how much rather depends on the numbers, which we haven't dealt with yet. But if this is going to take 9 units going down this way. Then this area has got 3 less than the 12, which was the other way, so that would be a float. The critical path is where there is no float, which will be the time that takes the longest, so that'll be the 8, 9, 12, 13, 14, 15. Now, looking at the same graph again, we can actually calculate float times and demonstrate the critical path by doing the following. You add a 2-cell box to each vertex of the network. That's to each vertex, including the start and the finish. So I'm going to do that here. You've got to be big enough to write a number in each half. So when you draw your networks, you need to make them big enough to do that. One for each vertex. Now, on the key down here, there's yellow on the left and blue on the right. We're going to do something called forward scanning now. That is a tidy version of what I've just shown you. We're going to do something called forward scanning, and then we're going to do something called backward scanning. Forward scanning involves finding the earliest start time that each activity has, and that number will go into the yellow box. Everything starts at 0. Looking at A first of all, because activity A takes 8 units of time, the earliest that C can start is 8. And the earliest that E can start is another one, which is 9. I would start looking down the other side now. The earliest that B can start is 0, but the earliest D can start is 6. Now when we get to F, we have 2 options. We can either go from C down the dummy, or we can go across from B to D is 2. If we go via the dummy, the start time of F would be 9. I'm going to write as a question mark because it may not be right. Going the other way, going BD, the start time will be 6 plus 2 is 8. Okay, 9 question mark, 8 question mark. You put into the yellow box the bigger number, 9. Because AC will take longer than BD, the earliest that F can start is when AC finishes, which is after 9 days. Similarly, for the start of G, this one here, well, that could be 9 plus 3 is 12, or it could be 9 plus 1 of F, which is 10. Biggest number goes in 12. 12 plus 2 is 14, more straightforward. 14 plus 1 is 15. That is forward scanning. Now we do backward scanning, where we go back. This time we start with 15, so finish at 15, so we have 15 there. That's always going to be the same. 15, subtract the activity duration this time. 15 minus 1 is 14, 14 minus 2 is 12, so far pretty straightforward. F, 12 minus 1 is 11, not the same as the yellow box. For this box up here, we've got 2 numbers. We could have 12 minus 1 is 11, 11 minus 0 for the dummy, or going the other way, 12 minus 3 is 9. Going backwards, we take the smallest value. Smallest value was 9. 12 minus 3 is 9, smaller than 11 minus 0. After that, it should be more straightforward. For here, 11 minus 2 is 9. For up there, 9 minus 1 is 8. This one has got to be 0, so 8 minus 8 is 0. And what that's told us is, first of all, that there's some float here and here. Secondly, that the critical path is where there is no float, which means 8, 8, 9, 9, 12, 12, 14, 14, 15, 15. That will be the critical path. There it is more tidily. And as I said at the beginning of this, float time gives activities some flexibility to when they start. So D, the earliest it could start is 6 and the latest it could start is 9, and so on. So that's that point there. More formally, EST, the start time of each activity, is in the yellow boxes. So that's the EST in the yellow boxes, and the latest finish time of each activity is in the blue boxes. EST and LFT. Not only that, but we can say the latest start time for any activity is the latest finish time minus the duration, and the float time is the latest start time minus the earliest start time, which is perhaps easier to remember as blue minus duration minus yellow. Another way of looking at calculating the latest start time for each activity, which is always important if you're on a building site and you want to get going with something and you're waiting for other things to finish first, you need to know the latest of your activity that you're worried about can actually start. The business of calculating float time. Latest finish time minus duration minus earliest start time. Zeros are the critical path. I find this table slightly more helpful than the table on page 414, but that's up to you. And that is what scheduling is all about, calculating the earliest start time, latest start time, etc. using a technique called forward and backward scanning. I'll put exercise 10b into another recording.